Buffalo is famous for a lot of things. Architecture, football, proximity to Niagara Falls. But let's be honest, nothing represents this city quite like the chicken wing. Today, wings aren't just food, they're a cultural icon. Visitors from across the globe take on the official Buffalo Wing Trail, sampling saucy favorites from dozens of local restaurants. From corner taverns to international chains, the humble wing has taken flight far beyond Western New York. But here's the twist. Wings aren't just a Buffalo delicacy, they're also a lesson in anatomy. In this episode of Compact Science, we'll dive into comparative anatomy to get a better idea of how muscles, tendons, and bones work. Chicken wings aren't just tasty snacks, they're science on a plate. What if I told you that the bones in that wing are related to the bones in your arm? You and a chicken have a lot more in common than you think. When you eat a chicken wing, you're actually holding a chicken's arm. The wing has the same bones as your arm, a humerus, a radius, and an ulna. The meaty drum is the humerus, while the flat piece is the radius and ulna. The tiny tip is kind of like the chicken's hand. Humans and chickens may look very different, but we're both vertebrates. We're animals with backbones and skeletons inside our bodies. Scientists call these similarities homologies. That means different animals share a body part because they had a common ancestor long ago. Over millions of years, those bones were shaped by evolution, allowing us to do different things. Chickens use theirs for flapping, humans use them for lifting and throwing, bats use theirs for flying with giant finger wings, and whales use theirs as flippers for swimming. Even dog legs follow the same pattern. Speaking of homologies, most humans have 7 bones in their neck. These are called cervical vertebrae. But what about giraffes? Their necks can be as much as 6 feet long. They also have 7 bones in their neck. They're just a lot longer. Bones themselves are amazing. They're strong but slightly bendy so they don't just snap. And they can heal themselves if broken. They give our bodies shape and help us move. They also protect important organs. For example, your skull shields your brain and your ribs guard your heart and lungs. Not every body part works the way it used to. Some animals still have little leftover parts from their ancestors, called vestigial structures. These are body parts that don't really serve their original purpose anymore, but they're still there. They're like clues from the past written in our skeletons. For example, humans have a bone at the end of their spine called the coccyx, or tailbone. From this, scientists have hypothesized that our distant ancestors once had tails for balance and movement. But today that bone just sits there, and we only really notice it if we fall hard on our butts.
Ouch!
Comparative anatomy is also super important for understanding fossils of animals that lived long ago, like dinosaurs. Chickens, for example, have little bumps on their wings where claws used to be. A throwback to ancient bird relatives that had clawed hands. When scientists dig up fossils, they often find only bones or even just pieces of bones. To figure out what kind of animal those bones belong to, scientists compare them to the bones of animals alive today. For example, when paleontologists discovered that some dinosaurs had wishbones, a kind of bone that only birds have, they realized that birds must be the direct descendants of dinosaurs. By lining up fossil bones with modern skeletons, scientists can trace how animals changed over millions of years. Without comparative anatomy, a pile of fossil bones would just look like a puzzle with missing pieces. Instead, we can rebuild entire creatures and learn how they lived. I'm here at the Buffalo Museum of Science with Paige Langle. She manages the biological collections here at the museum. How's it going, Paige?
Awesome.
Wonderful. All right, so tell us about the collections a little bit.
Sure. The museum manages over 700,000 objects in its collection, and I pulled some specimens from our vertebrate collection. That is a collection that contains about 45,000 specimens.
That's a lot of bones.
It is.
That's a lot of bones in the vertebrate collection.
These are cervical vertebrae, so these are neck bones.
Okay.
And these neck bones in particular are their top 2 neck bones. So this is an atlas and an axis from a giraffe.
Okay, so atlas, the dude that like holds the globe.
Exactly.
Okay, so it holds your head like
Exactly.
Okay, similar.
This holds up the skull.
And then axis,
This is what the skull kind of spins on.
Because you spin on an axis.
That's right.
I love it. Isn't it science?
So you can see with these giraffe bones, they're actually really elongated compared to the bones behind them, which are also an atlas and an axis, but these are from an elephant. So these tiny bones here are also an atlas and axis of a domestic cat.
It's like I got ones at home. Look
Me
at that.
too.
Oh my goodness. So wait, what else you got?
So yeah, we just showed you here the bones from a domestic cat. So we have more domestic cat material here. This is a full skeleton of a domestic cat, and we're gonna be looking at its skull. This is also a skull from a domestic cat. But this skull has been exploded so that you can see every single bone that makes up the skull.
That's an interesting word that you use there, exploded. All right. Wait. So you're telling me that a skull isn't just one bone?
It's not. Even though it looks like one piece, there's actually a lot of little bones that fit together like puzzle pieces to make the shape of the bone. And each of these individual little bones in the skull can change shape to serve a different function.
Okay, all right. So kind of like this. What is this?
This is a dolphin. It has a
looks very different from a cat,
wildly
right?
different shape.
A little bit, it's fine.
But it has all the same bones. So as we look at this cat skull, we can see the bone here is the premaxilla.
Okay, so like ooh.
Here, it looks like a nasal, but this is actually the change shape of the premaxilla.
So I would expect the nasal to be in the front, but no, it's
not. So the nasals are actually above that opening where you would be breathing in your air. So in a dolphin, that nasal hole has been pushed all the way back onto the top of its head. And you can see these are the 2 very small reduced nasal bones.
That's why the blowhole's there.
Yes.
Oh my goodness. How about this one? Ugh. So this is a bison?
This is a bison.
Yeah, okay. I just found it, it's nice.
Yeah.
So how does this one compare?
So it has the same bones as well. Here we have our premaxilla and the opening for where it's going to be breathing. And these are the giant nasal bones.
What? So premaxilla on our face, where would that be?
At the front.
The front, like right above our teeth and stuff?
Yeah.
That's
Yeah. Versus the maxilla here, that's where all of your molars will attach.
Actually, that makes sense. It's like, so right by our, it's like, oh, there's its teeth.
Yeah.
What are these guys?
So these are 2 skeletons that I brought out of very small animals. So right here we have a mole, and right here we have a mouse. And I'm gonna pull out their humerus.
Ha! That's funny. Sorry.
It's very humorous. So this is the humerus from a mole.
Okay, so humerus would be like this one, right?
Yeah, this is this bone. And from the mouse, this is its humerus. So you can see they're the same bone, but they look wildly different. So this is a really robust bone. It has lots of projections coming from it, versus this bone that's a little bit more thread-like.
So like those projections, that's where the more muscles can grab onto
Exactly.
it? Oh man, okay.
So the more projections and more robust the bone, the more area that muscle can attach, giving the mole the ability to be very strong when it's digging.
So it would win like a bodybuilding contest?
Absolutely.
Okay, all right, cool.
So here we have a Canada goose wing. And I love this specimen because it shows you how all of the feathers connect directly into the bones.
They do.
And this was prepared in a way so that you could see the bones. And you can see in these bones, this is the radius and ulna. These are the bones right here. And then this clump of bones right here are all the little bones in your wrist. And then these are the modified digits. So if I hold my hand up like this, that's kind of what you're seeing here. The thumb is reduced to just this little nub here. And then the other 3 fingers are fused together into this long bone. And then you can see this little tiny nub here is the remnant of the pinky.
Goodness. Wait, you said remnant. Does it do anything anymore? Or?
It doesn't. So that's what we would call vestigial.
Okay, all right, vestigial, kind of like our appendix. It's there, we don't need it.
Yes.
So I noticed you also have a bat here.
Yes, bats are also excellent flyers. They've just come at the problem a little bit differently.
I like how you say that. It comes at a problem. Okay, all right, it's like problem solving.
Yeah.
Biological problem solving.
Evolution is biological problem solving. If you look at their wing, their entire arm is involved in that flight. So it's not just these fingers, it's the whole arm. The radius and the ulna here that are separate in a bird are actually fused in the back to provide stronger flight.
Okay, all right.
And each individual finger is elongated so that those fingers can actually participate in flight and give the bat more agility.
And they're so cute too. Wait, and then these little guys on top. So that'd be the thumbs?
Those would be their little thumbs,
goodness,
which
so
you can
little.
actually see on the skin here.
Give my little thumbs up. Oh, they're so cool. They're so cool. Oh, well, thank you, Paige. This is pretty amazing. Every bone in this collection helps scientists piece together the big story of life on Earth, from dinosaurs to chickens to us. Now, it's your turn. If you are interested in learning more about bones, check out our Compact Science Viewer Challenge. We have a fun experiment where you remove minerals and make a chicken bone bendy. Get all the instructions on our website and be sure to share back your results. I'm Sarajane Gomlak Green and you've been watching Compact Science. Until next time, stay curious.
Compact Science is funded in part by the Joy Family Foundation.
I'm at the Buffalo. I said it on the front side. No, this is how it always starts. Humans and chickens. Instead, we can rebuild entire creatures and learn how they lived. Oh, sorry, that sounded scary too. Learn how they lived.